Okay. Hello, everyone. I will present you here our work titled Self-Adaptive Device Management for IoT using Constraint Programming. This work has been done with my supervisor and co-authors Sebastien, Bolle, Marc, Douet from Orange Labs and Eric Rutten from INERIA, France. In this presentation, I will start by presenting the general context of our work, then define the problem tackled in our paper. After that, I will present our solution with the proposed architecture, and then I explain on more details the target scenario. Thereafter, I will present the implementation and evaluation results, and then I will conclude by showing the main realization and some further items to extend this work. The general context of our work is the device management, which is the remote administration of users' devices at customer premises. And this is done by a configuration server. We call it auto configuration servers that sends out management operation to the customer, managed customer, we say customer premises equipment. And this communication between them is done based on some defined dedicated protocol, such as Towarzystwo and lightweight machine-to-machine protocols. The main management operation involves provisioning. It's for initial and in-live configuration, monitoring to detect anomalies using clock traces, maintenance for firmware and configuration updates, and troubleshooting to fix service and device errors remotely. By doing all of this, device management keeps devices connected, updated, and secure. However, DM solutions are widely deployed and used for smart home service management with home devices such as TV set-top boxes. But with the expansion of the Internet of Things that offers wide range of smart applications with large fleet of heterogeneous devices, and for environmental reasons such as increasing the lifespan of devices, considering device management for IoT environment become critical. But with the IoT, there's a new challenge raised. Speaking about heterogeneity as moving from limited set of device types to wide variety of devices, dynamicity by moving from rather stable internal state, speaking about battery network condition, to versatile states, privacy, where many IoT service leverage sensor data to keep to adapt to the local context. So it's critical to adapt the services to protect users' privacy. And finally, scalability as we move from few devices to massive number of devices. Thus, the legacy solution with manual management of fleet of devices solution is not adequate for IoT. Furthermore, the centralized solution that's based on cloud computing are not able to handle the fleet with large number of devices. So our solution was to move to autonomic and distributed device management for IoT devices. However, this solution consists of two main notions. The first one is the autonomic computing. The autonomic computing system is used to solve problems related to the complexity of managing resources by making adaptive decision-making high-level policies. And here we can see a MapK autonomic loop reference model for autonomic computing with autonomic element that manage the managed elements via sensor that gather information, send it to monitor step and after to the analyst to analyze this monitored information, then decide on the action with the planned step and execute them to adapt to the new state. And all this information is kept in some database, we call it knowledge base. By doing this, autonomic computing reduces human intervention and enable the system to adapt to unpredictable changes. There's many applications of autonomic computing in the state of the art of computer science, speaking about server load balancing, autonomic updating software, and etc. The second part of our solution is speaking about distributed device management based on edge computing. Normally, legacy DM solution were centralized in cloud that offers advantage of flexibility and on-demand resources, but however, it illustrated to the new class of IoT application as with a huge number of heterogeneous devices. The consumption of bandwidth is really significant, and as more devices appear, there's a need for a scalable solution to adapt to varied deployment scenario and enable seamless integration and management of the new devices. On the other hand, the edge computing that brings data processing power at the edge of the network and devices. So it's closer to the source of data. So it's answered the questions regarding latency, privacy, and bandwidth. So we believe that with edge computing with all its features fit well for device management for IoT devices. For this solution here, we present the proposed architecture. In the image, we have here two logical layers, the control layers with the managers and the infrastructure layers at the bottom with which provide the nodes and links to host server and client component for device management service. And for the control layer, it consists of two a manager, external one presented by the system administrator, and our autonomic manager, which we called auto-scaling manager. And there is a communication between these two managers at the beginning, we say at design time, to provide information regarding the DM servers, service and infrastructure information. And then whenever there is an important information to be passed to the auto-scaling manager. We will zoom in more for our auto-scaling manager to see inside it. It's follow the MapK reference model. We speak it about a little bit before, with all these models regarding monitoring and analyzing and the planner and executor one. The main objective of this manager is to scaling horizontally DM server, to add server and decide where to place them on the infrastructure, while at the same time optimizing the infrastructure resources. We will explain each part individually. So we'll start with the main component of the auto-scaling manager, the mapper, which is the planner one. The main model it's used at design time. It's mapper and remapper, so it's used at design time, and then whenever new information is observed and transmitted by the monitor. It relies on constraint programming solver integrated into feedback loop to decide on the placement of servers and clients. The constraint programming, here we have the mapper model, where the constraint programming used is paradigm used to solve combinatorial problem defined by a set of variables belong to some defined domains, with constraint over this variable to decide what values the variable could obtain, and an optimization objective that's be chosen to be minimized or maximized. Then a general purpose solver here will be used to provide a visible solution. This visible solution while satisfying all the required constraints. But this mapper model based on three main inputs coming from system administrator or from monitor. The first one is the DM service information. Here we presented the servers, DM servers and DM clients as a graph with nodes represent S, here server represented by S and clients by C, with CPU, RAM and location requirements and the communication links between them with bandwidth, latency and type requirements. The second information is the underlying infrastructure graph, which represented by node with available CPU and RAM, in addition to the dedicated zone, we call it DZ, which is the place where the node is found. We can find it in the infrastructure, and the physical link between these nodes with available bandwidth and latency. Regarding the objective, we decide for our model to use multi-objective function to adapt for DM system. Here we have many objectives with some coefficient. One of them will be activated at runtime. Sometimes it's decided by the system administrator based on the requirements. And we have here choose between two choices: minimizing the number of used nodes or minimizing the consumption of the total consumed bandwidth. This is the main part of the auto-scaling manager. The second one is the planner, the monitor. We'll return back to the monitor one. The monitor is responsible for observing evolution of past DM system and infrastructure and forwarding all this information to the remapper model. And the monitored information depends on the scenario we want to validate. So it could be infrastructure info regarding arrival and departure of physical nodes and reaching some resources threshold, or could be an external info sent by the system administrator to the auto-scaling manager regarding arrival or departure for some DM clients. And then, based on the information coming from the mapper, the planner will decide on the required action to move from the current system state to the target one, speaking about by extracting the difference between the current and target mapping for servers and the clients. To do only the necessary action, which we called it calculating the cost of migration from old state to the new states. And then the executor will be used to validate this action. Regarding the use case for our solution, we know that we saw that many different changes may result in the need for a new system configuration in the context of DM. So privacy is an important concern that adopted in our work. Here, a client may need to be managed by a specific device management server or a server placed in specific area, as we called it before, zone. Due to some privacy considerations, such as IoT devices belong to a private enterprise or for a VPI person. Thus, whenever a new IoT device is asked to join the DM service to be registered and managed by a server, these new devices will need some resources regarding CPU, RAM, and normal one, in addition to privacy one. So here in the image, we show a region in infrastructure with 3 different zones. Inside this zone, we have the nodes and also the physical links that connect them. And here we have 2 clients, C1 and C2, with the server that manage these 2 clients at design step, we say. Then the current configuration for this system is represented by this graph, with server and this connected clients that managed by it. However, at some time, maybe new clients asked to join the system, and this information will pass from the system administrator to auto-scaling manager. We have arrival of clients 3 that need to be managed by server in zone 1, and client 4 that need to be managed in server in zone 3. From our state, we know that the client 3 could be managed by the server S1 that's already running, but for the C4, we can't find a new server, so we need to start a new server in zone 3 and make him manage this new clients. So the new target configuration will be something like this. We have the new server S2 and its client S4, C4, while C3 will be managed by S1. So with the mapper, it could be here possible visible placement where we place the C3 in node 3 into zone 1, which be managed by S1 after. And here we start the new server S2 in node N1 in zone 3. And also we for the client 4, we install the DM client C4 in node 2. This is concerning the privacy scenario. Here we show the implementation choices. Okay, so we have mapper implemented by Chocosolver. We choose Chocosolver for Constraint programming solver in Java. For another one, we choose Python language, and the communicating between system and RabbitMQ, it's done by system admin, and another auto-scaling manager, it's covered by a message bus RabbitMQ. For the evaluation, we choose 2 different infrastructure, 20 edge nodes and 40 customer promises nodes, and the second one, 20 and 80 customer promises node. And this customer one hosts clients, and each will host server, and each come with more resources. For the resources capacity, it's inspired by Amazon EC2 instances type. We choose also different workload regarding the total number of clients from 40 to 100, and their arrival rate and service time following an exponential distribution. For the result, the first one, we check if auto-scaling manager can adapt the number of device management server at runtime to fulfill the device management client privacy requirements. On x-axis, we have the time, and on y-axis, we have the number of components. In blue, we have the number of clients, and in green, the number of server. At the design time here, we start with one server and 3 clients. And then we see that during the time, here at this point, for example, when the clients goes from 8 to 11, we see that the number of server goes from 3 to 5 to adapt this new clients joining request. But at some time, when some client departure the system, like here, we can see the drop in number of clients, but the number of servers stays stable because these servers still have another clients to be managed, so we still need them running. At the end of the evaluation, we can see that at the end here, we return to the initial step with 1 server and 3 clients. This is regarding the adaptation characteristic. The second one, speaking about acceptance ratio, to check the system ability to satisfy clients joining requests. Here we have on x-axis the total number of clients, and on the y-axis the acceptance ratio is the ratio of the accepted clients joining request to the total arrived one. We have also that we tested for the 2 different infrastructure, the blue with more resources and green with less. We can see here there's a drop as the total of number clients increased, but it's negligible because we use a waiting queue. So when clients come and we can't accept them, we keep them in a waiting queue for some time, and then we try again when there are some more resources free in the infrastructure. And also, it's really clear that using more power for underlying infrastructure leads to more acceptance ratio as we have more resources. Here also we can have the adaptation time, just to check the complexity regarding the time of our solution, how much. We have also total DM clients on the x-axis and adaptation time in seconds on y-axis. Here we have the whisker plot. We can see that when the total of number of clients increase, there's increasement on the consumption of time. However, we can see we all finish at 60 seconds and 1 minute because we strict our solver to find this solution within this time, not more. If it's not able to find, we stop the search. And also we can see the spread between here the median and the lower quartile is less than the median and the upper one, because that means that most of placement require more time to find the solution. So that's all regarding result. To conclude, here we provide distributed device management architecture for IoT at the edge. And for that, we provide an autonomic manager based on constraint programming solver, which follow the IoT fleet evolution at runtime only, and the proof of concept validation of the proposed architecture with a privacy scenario is done with the results. However, this work could be extended. One extension could be regarding the constraint programming model by adding more constraint, something like network connectivity type, and also considering infrastructure evolution at runtime, speaking about failure of node and joining node to the infrastructure, and also considering another scenario like DM server limitation and reaching infrastructure resources thresholds. Thanks. That's all from my part. Thanks for listening.
Thank you for the presentation. I have a question. You have done some researches about efficiency, time parameters, etc. You presented it as a result, but have you any practical implementation, maybe as a pilot of your solution?
Okay, you mean to speak about real things, not simulation for the result?
Yes.
Okay, I would like to say that because our work is, as we know, it's the first work regarding distributed device management of IoT, so we don't have really some real information regarding this. The only thing we had some centralized solution provided by Orange Lab, which was a basic thing, but it was centralized. That's why we were working on Orange Lab to provide distributed one, to not stay in the cloud, as there's a lot of resources and the consumption. So we didn't have any real work or some real numbers to use for our work, because it's we can see there was some previous step to start this work, but it's really the first work in this direction. So we just make something in random manner for the numbers.
Thank you.